All right, so let's start with the second half of the course, where we'll talk about probability, which is kind of the other major topic we are focusing on in the Toolkit course. Like linear algebra, we'll spend a little bit of time developing some basics, but we will keep seeing some small applications as we go through the lectures. And this is sort of one of the other mathematical tools, which I think is probably useful in kind of graduate level research in computer science in general. We'll also treat this somewhat abstractly and still emphasize proofs and so on, but let me know if anything is unclear, or if you want me to spend more time on some part, and yeah, we can see more as we go along. Small announcement. Homework 3 will go out later today. So yeah, just look out on Canvas for a more detailed announcement and the posting of the homework. Okay. And it'll cover a mix of some linear algebra questions and some probability questions, which we'll be just talking about in today's lecture and maybe on Thursday. All right, so in the setting of probability, the kind of basic object, and we'll start with what is called the finite setting. So so I mean, my view of probability is, of course, is that in some sense it's a way of formalizing reasoning under uncertainty. So we want to talk about some processes, some things maybe which we are doing if we are running some sort of a randomized algorithm which takes data but looks at it in a way which might depend on some sort of external things which we haven't completely planned, and then sort of we model roughly the lack of certainty we have about what that algorithm will do is some kind of randomness. If we know some things about intuitively what is it more likely to do and what is it less likely to do, etc. And or it can be just something which is happening in nature in some sense and we are observing. So maybe the data itself that is coming at us is random, and well, data is not necessarily the most natural thing to observe in nature, but it's common when you're sort of doing computer science. It could be kind of weather patterns, it could be some other processes, it could be stock market, it could be sort of pretty much anything we are looking at, but we are not quite sure exactly what we will get to see. Okay. And the way this is modeled is we think of a space of outcomes. So these are pretty much everything we want to allow for the possibility of happening. And this depends on the problem. So if you are tossing a coin, you could say that the outcomes are whether it comes up heads or tails. You could also say that the outcomes are sort of how many times it spins in the air before it lands on a surface. So what angle does it hit the surface at when it first lands there? What is the kind of displacement of air molecules because of the coin? And all of these we may have some uncertainty about, and we may care about one or the other. We may not necessarily care about the displacement of air molecules, but we may care about the angle with which it hits the surface. Or we may only care about whether it lands up heads or tails, or sort of what happens. So these are just all possible kind of outcomes which we want to include in our view of the world. And this is what we will call the outcome space, or sometimes called the sample space.
So the sample space is the outcome for one of these situations or for all of them?
What do you mean by one of these situations?
So you described, for example, the angle the coin hits a surface, or whether it lands heads or tails, or how many times.
Right. So the outcome space includes all the information that we want to think about. So, and that's a good point. So if we, let's say, care about whether the coin lands up heads or tails, and we care about the angle with which it's going to hit the surface, and we care about the number of times it spins in the air before it lands, then the outcome space will include all this data. It will have sort of a possible outcome when it kind of only spins up sort of 3 times but lands head. It will also have an outcome corresponding to when it spins 5 times but lands heads. It will have an outcome for when it kind of spins 3 times and heads tails, or 5 times and ends up tails, and so on. So, and likewise for the angles. So, okay,
got it. Thank you.
So yeah, we will think of the outcome space as capturing all the information that we could possibly be interested in. Okay. And yeah, we'll later see that if you're only interested in one of these things, these are what are called random variables defined on this outcome space, and we'll get to that in a bit. Okay. But outcome space is all the information. And here we are assuming that the outcome space is finite. So we are not necessarily writing down information which can sort of vary in infinitely many possible ways. So if I'm writing down the angle, let's say I only care about the multiples of 1 degree, but I'm not thinking of the random variable as a continuous, or the angle with which it hits the surface as a continuous, as a number, just let's say between 0 and 2 pi, which can be anything. So so I'm only limiting myself to outcome spaces which have finitely many outcomes. Okay. May not always be the case, and we'll see later how to properly deal with cases of infinite outcomes. But for now, let's make this assumption. Okay. Any other questions? The other thing which we need to define a probability space is some notion of quantification about which outcomes are more likely, which outcomes are less likely, and so on, or sort of basically some comparison of different outcomes which captures our belief about or what we know. And this is again part of the modeling of the problem. So we may know it's a fair coin, so we think that all outcomes like the heads and tails will be equally likely. We may also know from previous experience when we usually toss coins based on how strong is the flick of our thumb and sort of where we are standing, maybe we may have some understanding of whether it's more likely to spin 3 times or 5 times or 7 times, etc. Okay, so this is again capturing our knowledge of some sort of prior knowledge we have of this uncertainty, and this is what is called a probability measure or a probability distribution. Probability distribution. Okay, and this is thought of as a function which assigns some value to every outcome. Ideally, we want the values to be at least non-negative, and so we can compare the values assigned to 2 outcomes and think of if the value for one outcome is twice as bigger as the value for some other outcome, then we are going to think of that outcome as twice as likely. And it's convenient, as we will see, to have a normalization condition that all values add up to 1. So then, because they're non-negative, they're numbers between 0 and 1. So that's what we will think of as a probability measure or a probability distribution. So a probability space for now is specified by 2 objects, the outcome space and a probability distribution or probability measure on the outcome space. And then we will work with it to define other properties and so on. And we'll see how to extend this when we have infinite possible outcomes, etc. Any questions about this? And these will be my usual notations. We will denote, so in this sort of slightly wobbly grid, each square is, or each cell is supposed to denote 1 outcome, and I'm going to use little omega to index 1 specific element of this set capital omega, okay, which is any individual outcome. Okay. And the next thing I want to define is events. And an event is nothing but a subset of the outcome space. Okay. So any subset A of omega, which is in this sort of grid drawing, again, a bunch of cells, is what I'll call an event. Okay. And we might want to care about some of these very special events, which are just subsets which contain exactly 1 cell. So for a little omega, we can look at a set which just contains that 1 cell corresponding to little omega. And these are sometimes called elementary events or atomic events. And we'll see that sometimes when we have infinitely many outcomes, defining these elementary events will be problematic, but we'll still be able to work with events in general. Okay. And we'll get to that later. Any questions about the definition of an event? Okay. So I should say, I mean, I guess all of us have some notion of how to deal with uncertainty, how to quantify what is more likely or not. And this is just trying to define a formalism for it so that we can all be in the same page when we are trying to discuss these sort of objects in a somewhat precise mathematical way. Okay. And one other concept which comes up is what is called a random variable. And yeah, here I don't like the name as much because it seems it's a little bit of a misnomer in the way I want to think about it. A random variable, and for now I'll talk about so-called real valued random variables, and we can talk about random variables which are vector valued or sort of valued in some other set, etc., some subset of real numbers, etc. But let's think of a real valued function. So a random variable is just a function mapping the outcome space to real numbers. Okay. So it's just in each cell you have written down a real number. So you could write down 3 here, root 2 here, minus 1 over pi here. So it's just a function. So for every outcome, it has a real number written in the cell corresponding to that outcome, and that just defines a function from the outcome space to real numbers. Okay. And so in this definition, a random variable is neither random nor a variable. It's a function, and there is nothing random about it in the sense that if you tell me the outcome space, the function is completely given. And yeah, I mean, to define it, I'm not even using for now the definition of new, etc. Why it is called a random variable is sometimes if you, so let's say coin tosses and so on, if I tell you exactly what happened to the coin, how many times it spinned in the air, how many what angle it hit the let's say my desk at, and whether it came up heads or tails and so on. If I tell you that, and if I ask you to compute, if I ask you, did it spin an odd number of times or an even number of times? There is nothing random about it if I told you what happened to the coin. This is completely determined, and you can tell me whether it spinned an odd number of times or an even number of times. And let's say we assign the number 1 to odd or 0 to even. And so you can output 0 or 1 based on what happened to the coin in terms of the outcome space. Okay. So if you know what outcome happened in the outcome space, you know exactly how to answer me as and give an output of 0 or 1. On the other hand, if I, for a second, suppose you know what happened in the outcome space, but I don't, and I'm just watching you toss these coins, look at something in the outcome space, maybe hidden somewhere, which I don't get to see, and you tell me whether it spinned an odd number of times or an even number of times. So I'm just seeing the output of this function, and I get to see that, okay, it's not always odd and it's not always even. It's there is some chance that if I see you do this many times, see that, okay, maybe 70% of the time it seems to be odd and 30% of the time it seems to be even, for whatever reason. So then I think of the output of this function as random if I don't know what's happening in the outcome space, and if I'm just looking at the output of this function, and that is why sometimes it's referred to as a random variable. So if you have a distribution on the outcome space, which tells you which outcomes are more likely, this induces a distribution on the range of this function. So whatever subset of real numbers, I mean, because the outcome space is finite, and for every outcome there is going to be one real number this function will give me, it will have some finite subset of real numbers as its range. And I can compute how likely each output of this function is based on what I know about the likelihood of all the outcomes in the outcome space. So in that sense, I can think of a distribution for the outputs of this random variable or the outputs of this function. And I still want to think of this kind of slightly funky way of getting a distribution for this random variable, because on the same outcome space, we might be able to define many random variables. Random variables are things about the outcome space, maybe at a given point we are interested in observing. So outcome space you can think of as modeling all the uncertainty of everything we could possibly care about that is happening in nature. And the random variable is capturing one aspect of it which we are interested in measuring in some sense. So maybe I'm interested in odd or even number of spins. Maybe someone else is interested in whether it came up heads or tails. Maybe someone else is interested in whether the angle at which it struck the desk was acute or obtuse, or so on. So it can be many different aspects of the outcome space which can define different random variables. And the notion of random variables actually generalizes the notion of events, because you can always think of an event as a random variable which takes values only 0 or 1. So the example I was saying, whether the number of spins in the air was odd or even. Because if you have a subset of outcomes, you can always define a random variable which is 1 if you have an outcome from that subset, 0 otherwise. So you can always think of an event as a random variable. And likewise, if you have some random variable which always takes values 0 or 1, then you can think of a subset let's say where it takes the values 1. So it's a function. I can define what are the inputs on which the output is 1. So that's I'll call y inverse of 1. And this is a subset of the outcome space. So the notion of random variables as a special case captures the notion of events, and this will be convenient to work with sometimes. These 0-1 random variables are called, often referred to as indicator random variables. Indicators of some event. Okay. Any questions about this? Okay. Now, we'll make our way through some kind of concepts defined for random variables. An important concept is expectation of a random variable, which is nothing but essentially some way of formalizing what is the average value this random variable takes. Okay, and you can think of like this value is just an average or sum or weighted sum of different outputs, where we kind of look at every output and the value on that output, and then multiply it with the likelihood or some weight we assign to how likely is that particular how likely is that particular outcome in the outcome space. This may not be a value that the random variable ever actually takes. You can have a random variable which takes values only 1 or -1, but when you look at this weighted average, the average is 0. That doesn't mean that the random variable ever takes the value 0. It's just that the average of the values it takes is 0, which in this case would mean it's equally likely to take the value 1 or -1. Okay, and let me just say, there is nothing special about random variables which take values which are real numbers. Well, there's something special that we can add these values and define an average. But we can define random variables which take values in whatever set we want. We may not always be able to define an expectation for it, because when defining an expectation of a random variable, we are saying we have to be able to take the value of that random variable and multiply it with some number which is between 0 and 1. Okay, so and if the random variable takes a value, let's say if I walk into this room, what is the first object I see? It could be, let's say, desk or a chair, but it's not clear what it means to multiply a desk by 1/3 and a chair by 2/3. So we have to be able to multiply these values with some numbers between 0 and 1. So that way it will be convenient to have values which are real numbers. Again, if the values were in a finite field, we can't quite multiply them by real numbers. But if the values were vectors, if the values were special case rational numbers, matrices, anything which we can multiply with a real number is a fair game in terms of defining expectations. Okay. Any questions? And this is sometimes written in a slightly different way, which might be more convenient to work with. You sort of group this summation by all the values that you see. So A is a possible value of the random variable. So A is in the range of X. And we group all outcomes together for which the value is exactly equal to A. And this is, as we said, this actually gives us a distribution for the random variable. So here we will think of this as a likelihood of the sum of all outcomes, the sum of likelihoods of all outcomes which result in the value A as the probability that the random variable takes the value A. Okay. So you can write it in this way, which sort of completely abstracts out the outcome space. It only works with the distribution induced on this random variable itself. So if we just know that the probability of the value 1 is 1/3, the probability of value 0 is 1/10, the probability of value -1 is 1/6 or something, etc. So we can completely forget about what the outcome space looks like if we just know these probabilities of X being equal to some A or not. Another way of saying it is that we can actually just change our outcome space to just the range of X and define a new distribution there and work with that. Okay. It may be suitable in some case. We may need to work with many different random variables defined on the same outcome space. So one or the other definition might be more convenient to work with. Any questions about this? Okay. A very simple but surprisingly useful property of expectations is that they are linear. So in particular, if you look at two random variables, X and Y, you can define a new random variable, which is X plus Y. Okay. If you think of these as functions, we know how to add two functions. On every input, add the output values of these two functions. And so X plus Y is a new function or a new random variable. Similarly, C times X is a new function or a new random variable, which pointwise multiplies every output by C. You can check, and then we'll see in a minute, that if you look at the expectation of this new random variable X plus Y, it's actually just sum of the expectations of X and Y. And actually, we can state this in a language we already know. We kind of know what these properties usually define. So if you look at expectation, it's a map from the space of all functions, let's say real value, and it maps them to a single real number. So it takes as an input a function, and it defines a real number. You can check that this is a vector space. And let's call it V. And this map is a linear transformation. And because it's also a vector space over the field of reals, and it's a linear transformation mapping a vector space to a single real number, by Rees representation theorem, we actually know that it can be written as an inner product. So think about what inner product we can write this as. Okay, I'll leave that to you. But it's it is in the language of linear algebra, it is a linear transformation. And let's see the proof, let's say, of this part. Here, it kind of shows that maybe different definitions are more or less convenient to work with. So this property is very easy to show with the first definition, not so easy with the second definition. The first definition of expectation, it's kind of, the expectation is just the summation over outcomes, the likelihood of that outcome, times the value of the random variable X plus Y at that particular outcome. And the value of the random variable X plus Y is just the sum of values of X and sum of and Y at that particular outcome. And then, yeah, it's just using distributivity. The proof of the other property is very similar. Any questions about this? Okay, so let's see an example. And so we'll try to kind of define all the objects we talked about and then try to capture some sort of random experiment we are interested in. So suppose you started with a deck of cards, which was maybe in some fixed order. So maybe sort of all suits were arranged in some ascending order, and sort of you had the card arranged by some specific maybe clubs was first, and then spade and hearts or whatever. So it's arranged in some specific order. Okay, and now suppose we shuffle this deck to end up with what we think of as a completely random order, and then we'll need to formalize this, but we'll see what's a good way of doing this. But yeah, so we want to formalize some notion of sort of a completely random ordering of let's say all the 52 cards in a deck, and then we ask the question of how many cards are in the same place as they were, or sort of in the order. Let's say some card was in the 10th position, and then after we did all this shuffling, cards sort of went around, but let's say this particular card still ended up in the 10th position. Okay, things above or below it might have changed. And how many cards does this happen to? Is the question okay? Yeah. So this class will try to model or formalize a lot of things. So yeah, please do unmute yourself, speak up so that we can try to figure out what's a good modeling. Let's say we have n cards so that I don't have to write the number 52 again and again. Any suggestions on what we should take the outcome space omega to be?
Naively, it could be the all permutations of cards. So that's n factorial.
Yes. So it can be the space of all permutations of n objects or n cards. And there are n factorial such permutations. So this captures all the information about what we want to study in this experiment, because in particular, it's a space of all permutations. So a single outcome is one permutation of all n cards. So it tells you the ordering of every single card where it appears in the deck. And if I know this, I can certainly figure out how many are in the same place as before. So this outcome captures all the information that I wanted to capture. It could also be a simpler space. It could just be the space of exactly the numbers 1 to n, because each of these outcomes would tell me how many are in the same place. But it will be a little harder to work with this space, because the distribution on this space is actually what we are trying to find. In fact, we're just trying to find the probability that, so we are trying to find some specific average over this space. So it could be the space of numbers between 1 and n, which will tell us how many cards are in the same place. Or it could be something else. But this is a clean enough space where we know how to calculate the probability distribution nu on all permutations in a way to capture our intuition of a completely random ordering. And we know how to do this without really doing too much computation. It's so that is usually what will govern our choice of a probability space. It's something which captures all the information, and it's something where we know how to write down the probability distribution relatively easily. Okay, maybe there are other spaces we could work with, but yeah, maybe they are more complicated. In particular, if I look at the space of numbers 1 to n, which define how many things actually landed in the center, I don't know how to calculate the distribution on that yet. It's okay. Any questions about this? So that's one option, not the only option. Yeah, for example, you could also have an outcome in the space, how many times did we actually need to sort of shuffle the deck of cards, and how many, yeah, I mean, so there can be other information which we are not choosing to capture in our definition of outcome space, but we want to define an outcome space which captures all the kind of relevant information. And here we are going to say our notion that we have a random ordering we will capture by saying that all orderings are equally likely, or sort of for all outcomes omega, we will capture its the value the probability distribution gives to it as 1 over n factorial, so that all outcomes will have the same value and they will add up to 1, okay, the n factorial outcomes. Okay, so that goes for the probability space. Now let's define a random variable which we want to study. So let's say we define x, which is a function on outcomes. So if I tell you exactly what is the final ordering you ended up with, you know how many cards are in the same place as they started out with. So you don't need any extra information. You can just compute this as a function of the final ordering. Okay, and suppose you always remember the initial ordering, so that, let's say, is just fixed for the entire problem. Okay. So this is a random variable we want to study. This is also known as the number of fixed points of a random permutation, if you want to state it in that language. Okay. And one thing we know for sure is that this outcome depends on the ordering. It's not something which is independent of what omega we are given in, or in other words, there is some uncertainty about the number of cards in the same place if we don't know the ordering a priori. So it's not something where I can just tell you that no matter what you do, there will be 5 cards in the same place as you started. So what we'll compute here is the average of this. So what I'll call, on average, how many cards stay in the same place, or in expectation, how many cards stay in the same place. And again, this is not, at least to me, sort of an immediate thing to compute, but you can write it in a way which makes it very easy to understand. So we can write it as so for each card I, we can define a variable which is either 0 or 1 based on whether that card I stays in the same place as it was before we started shuffling, or it moves. Okay, I mean, it sort of moves and ends up somewhere else. It could move and end up in the same place, in which case we will still say that it's the indicator is 1, it ended up in the same place. Okay, is that, and since we are counting the total number of cards, we'll just sort of, for each card, we will ask whether this is in the same place or not. The second one is in the same place or not. 1 to n is just some arbitrary labeling of all the cards, maybe according to the initial order if you want. And now, the nice thing is linearity of expectation. So and note that, I mean, in case you know what independence of random variables is and so on, so there are properties of random variables, but for linearity of expectation, we don't need anything. Sort of whenever you have a sum of random variables, you can write the expectation of the sum as the sum of the expectations. That's it. It's always a linear transformation. We're not using any properties of how these random variables are defined, just that the sum is what we are studying. Okay. But the nice thing is, it sort of reduces the question of understanding this complicated random variables of how many things are in the same place or not, to studying a very simple random variable, which is only takes two values on either 0 or 1, and it's sort of really about this one card. And if we just understand all of them, we can just add them. Okay. Any guesses on what expectation of x1 is? This I claim we can compute relatively easily.
One over n minus 1 factorial, because you keep that card fixed and you shuffle all the others.
Right. So it's not 1 over n minus 1 factorial, but it's n minus 1 factorial divided by n factorial. Because there are n minus 1 factorial ways in which this card could be in the same place as it was when we started. Let's say it was in the first position. What does it mean for it to end up in the same place? Well, it will have to be in the first position. You know where it's going to go. And I'm not sort of restricting the ordering of any other cards in any way. So the other cards could be in whatever order you want. In particular, there are n minus 1 factorial orderings of the remaining n minus 1 cards. And we have started with the probability space that all orderings are equally likely. The probability of each of them is 1 over n factorial. So the expectation of x1, or the likelihood that the first card ends up in the same position, is n minus 1 factorial, which is the total number of events that we are summing, times the probability of each event, which is 1 over n factorial. And so this is just 1 over n. And it's the same for each card. Use the same argument. You want to keep the third card in the same place? Sure. Let's fix the third position and then organize, sort of order the other cards in whatever way you want. The third card will be in the same place because I just kind of fixed it and nailed it there in some sense. So each of these expectations is 1 over n. And so the expectation of n, or the expectation of x, is equal to n times 1 over n, or 1. So in expectation, one card will be in the same place where we start. If you try to calculate the kind of likelihood of every outcome of x, of what is the chance that two cards are in the same place, what is the chance, then it's sort of more complicated. You have to say the chance that some 5 cards are in the same place. You have to first go and fix, okay, which are these 5 cards which are in the same place, then shuffle the others. And you have to make sure that exactly 5 cards are in the same place. So it's not that maybe 6 cards ended up in being in the same place, etc. So you have to be a little careful when you try to calculate the probability distribution of all possible values x can take. But to actually understand its expectation, we don't need to do that. We just need to understand these very simple random variables, which are just about one card at a time. And then linearity of expectation carries us the rest of the way. Any questions about this? Yes, I'm really belaboring this possibly simple example, but in some sense, this is an extremely useful way to think about random variables as the sum of simpler random variables, and then applying linearity of expectation kind of reduces our task to understanding a very simple random variable, which usually just depends on some local things and is much easier to calculate. Okay. All right. One other operation which we do in probability spaces is what is called conditioning. Okay. And in some sense, conditioning is nothing but just sort of updating our knowledge about nature, or updating our knowledge about the problem we are modeling. So suppose I know that so it's kind of, I toss this coin, and suppose this coin sort of, I know that it came up, sort of it spinned an odd number of times in the air. Okay, I still don't know the rest. I don't know maybe where it sort of what angle it hit the desk at, and I don't quite know whether it came up heads or tails and so on. Well, actually, okay. So yeah, suppose I don't know how I started. Otherwise, if I know this number of spins, I know what it ended up as. But let's say I don't know that. So it's saying that if I know that basically I am only working with a subset of the outcome space, somehow I kind of got this additional knowledge based on maybe some information that kind of leaked about the environment, then I can update the state of my knowledge by just saying, I'm going to just assign a probability of 0 to every outcome that I know did not happen or is not going to happen. Suppose I just sort of know something about this natural process, and suppose for whatever reason I have a coin which only spins an odd number of times, and it could be any reason why we are going to update our knowledge, and depends on the problem. And so we are going to zero out the probabilities of everything which is not happening. And let's say we're only sort of affecting, or sort of your only knowledge is kind of what outcomes came and what didn't, and we're not really changing sort of the likelihood of the outcomes that, or sort of the relative likelihood of the outcomes which could happen or which are in A. So what we are just going to do is divide the probabilities of all the outcomes that can still happen by the total probability of all outcomes in A. So so that the sum is still 1. And so this gives us a new probability distribution or probability measure on this new outcome space, which is just A. And so conditioning on an event A is just restricting our probability space to A and maybe redefining our probability measure to work with it. Okay. And there are a couple of pieces of notation to sort of indicate this. Here I'm denoting the probability measure on this new outcome space A as just new sub A, which is defined by starting with new on the original outcome space and just kind of modifying it by restricting only values to A. The probability of an event B conditioned on A is kind of indicated this way, which is, yes, according to the new distribution, what is the probability of the event B? Okay. And similarly, the expectation of a random variable X in this new outcome space is just indicated as expectation of X given A, which is nothing again, but do what you were doing earlier, but just now changed your probability distribution to this new distribution, new sub A. Okay. Any questions about this? Okay, let's take maybe a 2-minute break and then we'll continue with this concept a little more. Okay. Any questions that came up in the break? Let me sort of point out one other way that is common when thinking about conditional probability or the probability of B conditioned on A. And this is usually thought of as, so let's just write the summation that we have. So our new outcome space is A, and everything outside of A has 0 probability according to this new measure. And for outcomes in A, the probability values are so actually, yeah, let me write it more slowly. So we are interested in the probability of B according to this new measure. So the definition of that is just add up the values of all outcomes in B according to the probability measure. and we will get a non-zero value if and only if the outcome was also in A, because otherwise we will get a zero value. We just sort of changed new A, or that's how new A is defined in terms of new. And so another way of saying it is that we are looking at all outcomes in B intersection A. And dividing by the probability of all outcomes in A, which is where our kind of normalization for making things sum to 1 was coming. This is sometimes also stated as a definition of conditional probability. Yeah, I mean, they are equivalent. You can work with whichever you find convenient. But yeah, I'm just stating it as a way of just defining this new probability measure. Another notation that is common is sometimes instead of B intersection A. So B and A are sets, right? They are subsets of omega. So you can think of intersection as just another set. But sometimes instead of set, you think of them as kind of logical statements with a yes or no answer, and you sort of, it's written as B and A. When you think of an event as being defined by a logical statement, the coin came up heads and it struck the desk at an acute angle. Okay. So formally by that we say that the set of all outcomes where the coin came up heads intersected with the set of all outcomes where the coin struck the desk at an acute angle is the set we are talking about. But yeah, saying it in terms of sets and intersections sometimes can be a mouthful, and then we just use the either the English word and or the symbol for and, which is this wedge. Okay. Any questions about this? This is just notation in terms of condition. Another important thing I should say is that this conditioning is only defined if the denominator is greater than 0. Otherwise, it doesn't make sense. If I'm restricting my outcome space to some things which I know can never happen, it's not clear what I am trying to define here. Okay. Something which I'll ask you to check from definitions is what's called the kind of law of total probability or total expectation, that if I'm computing the probability of all outcomes in B, and let's say B is some set of outcomes, let's say B is these 4 outcomes, then I could directly compute it. I could just add the values of nu for all these 4 outcomes, or I could look at the distribution according to A, which is this kind of green cells, and compute the probability of B according to the distribution, which is sort of limited to lie only in the green cells when I sort of change my probability space, and then do the same for the red cells, which in this case I'm denoting by A complement, which is everything outside A. And I can sort of count these blue cells by counting, or sort of I can look at the probabilities of these blue cells by looking at them separately within the green and red cells and then adding them up appropriately, or I can directly look at them as in the whole space. The same goes for expectations. I can calculate the expectation according to the conditional probability distributions or the conditioned measures on A and A complement separately and add up these conditional expectations, or I can just calculate the expectation over the whole space. And we'll see that these are fairly useful ways of thinking about conditioning of this. And A and A complement were just two pieces of the outcome space, which were disjoint and which covered the whole space. And in general, you can think of a partition, which is just K disjoint subsets such that their union is everything. So that's just what a partition is. And you don't have to necessarily just think of splitting or dividing the space into two parts, this green and red regions, but you can have K regions or sort of K subsets of outcomes. And as long as they're disjoint, you can write the same, you can do the same computation. And notice that the second statement implies the first statement, because an event is in particular some random variable which takes a value 0 or 1. So this statement actually implies this statement. So I only need to define it for expectations. The one for probability is just follows from it, because if you have a random variable which takes 0 or 1 values, then its expectation is actually just equal to the probability of the event that it's equal to 1. Any questions about this?
Yeah, this might be obvious from what you're saying, but you're saying that the kind of first equation you wrote here, the probability of B in terms of the probability of B in terms of the probability of A, and then the probability of B given the probability of complement of A. You were saying that was one way as opposed to a different way. Could you, what was the different way of doing it?
Right. So one way is just I look at all the blue cells and I add the value of nu over of all the blue cells. I add the value of nu. This is one way, which is according to the left-hand side of this equation. Right. The other way is that I restrict my probability space to A, and I only look at the blue cells inside A, and I compute according to the conditional distribution, and then I multiply it by the probability of A, and then I do the same computation similarly for A complement, and I multiply it with probability of A complement. So these are two ways of computing the probability of all blue cells or all cells in B. And I claim that these are equal. So, I mean, it's when you expand out all the values of nu sub A and the probability of A, you'll just see that this is just rearrangement. Nu sub A is defined as nu of omega divided by probability of A. So this part will just cancel. This probability of omega will just cancel with the denominator I have in defining nu sub A, and you will just get nu of omega for A intersection B. So what this expression will simplify to is summation of omega in A intersection B, nu of omega plus summation over omega in A complement intersection B, nu of omega. And that's just all cells in B, because you're kind of adding the intersection of B with A and with A complement, that is all of B, right?
Okay, yeah.
Yeah, so I mean, it's not a difficult proof. It's just sort of opening up all the definitions. And yeah, sort of you can check that this equality holds. All right, now let's see another simple application of conditioning, which sort of again, partly as a modeling exercise in how we think of some random process. So let's say I invested some money in a stock, and yeah, in retrospect, we'll see that maybe it was not a smart decision to do this, but in some sense, I invested my money in a stock which on each given day, it sort of randomly goes up by 1 or goes down by -1, and the value of the stock goes up by $1 or goes down by $1, with probability half. So each of these outcomes is equally likely on any given day. Okay. And on every sort of, and I have some investment strategy, some complicated algorithm which sort of looks at how much money I have invested today, maybe also looks at what happened over the last 5 years in the stock market, in particular, what happened to this particular stock. Maybe it looks at the values of 10 other companies, whatever. It can be an arbitrarily complicated strategy. Okay. And I'm just trying to understand how much does this gain on my investment. So let's say I sort of invested some $N, then how much does it grow? So and let's say the value of the stock is large enough that it stays a positive number. So let's say it's bigger than 365, so that even if it did fall by $1 every day, it would not be a negative number. So let's say all of that is there so that I don't have to worry about those kind of issues. Okay. And now I want to understand how much does this investment strategy get? Okay. So is the so X is my gain. How much did I sort of gain by investing in this stock? And yeah, I can choose to do whatever, buy, sell, kind of sort of partly sell, or sort of essentially whatever I want to do with my money. But and it can depend on whatever information I choose to care about. Any questions about this?
Is there a notion between different random variables that do we consider whether x1 and x2 are independent or not? Is there a notion of independence?
Right. Good. So so we haven't yet defined independence, but yeah. So but here I'm not really assuming anything about them. I'm just saying the way the stock market changes doesn't really depend on what I am doing. The market doesn't care about me. I might care about the market. So X2 might depend a lot about like whether maybe if I had a lot of gain on the previous day, maybe I just get too excited and maybe I invest more money. So, and then depending on what the market did, I might, so let's say I have a strategy that on the first day, if I gain $1, I'm just going to go all in and invest a lot of money on the second day. Okay. So in that case, on the second day, I might have a lot of gain or a lot of loss. And this might depend on what I did, what happened to me on the first day, whether I gained $1 or not. Okay. So X2 can depend on X1 depending on what investment strategy I have in mind. In the sense that, yeah, how I choose to invest based on the outcomes previously can introduce some arbitrary, complicated relationship between these random variables. And we'll see what the absence of this relationship or independence formally is. But here I'm not assuming anything. Okay. Does that answer your question?
So here we are assuming that x1 and x2, like all those events are, all those random variables are independent.
No, we are not. See, okay, let's come back to this example maybe after I've defined independence so that we can discuss this in a more formal way. So let's first define independence, and then we'll discuss the example again. So independence kind of says that the probability of an event doesn't really change. The independence of two events A and B is saying that the probability of an event doesn't really change whether I'm looking at the whole space or at the space restricted to this event A. Okay, so the probability of, let's say, yeah, what I said is equivalent to saying whether I restrict my space to A and then look at the probability of B, then look at the probability of B, or I just look at the probability of A without or probability of B, sorry. So if I had this prior knowledge that I am within the universe given by the set A, or if I don't have this prior knowledge, in either case, the chance of B happening is the same. Okay, and this is equivalent to saying by our definition of conditional probability, or by one of our definitions, that the probability of A intersection B or A and B is equal to the probability of A times probability of B. And there are subtle differences. I mean, the center definition you can write even when the probabilities of A and B are 0. The definitions on the two extremes you can't quite write in that case. But when the probability of one of the events A or the probability of event B is 0, the center thing is trivially true. So it doesn't really change things. Okay, but you can remember either of these two definitions. Just apply with care. And similarly, we say two random variables are independent if the event that the random variable capital X takes the value little x, and the random variable and the event that the random variable capital Y takes the value little y are independent for every possible value X and Y that these random variables can take. Okay, so we defined the notion of independence for events with just that the probability does not change when I kind of restrict my universe to one of these events. The probability of the other event does not change. And for random variables, I just defined it in terms of all these events, which are what is the event that the random variable capital X takes the value little x. Equivalently, it's just a subset of omega such that the value of this function on this input omega is equal to little x. Right? So this is a subset of omega and hence an event. Okay. Is the definition of independence clear? Okay, and now let's go back to the previous example. And now x1.
Sorry, just quick, quickly. Was x and y, or on the next slide, was little x and y? These are events, right?
These are values. These are just values. So these are just real numbers in our examples. Okay. So.
Okay.
So a random variable is a function which takes a value which is equal to a real number. So we are just saying what is the chance the value of this function is equal to this real number little x. Okay.
I see. Okay.
Good. Now let's go back to the previous example. And here I'm saying on the first day, if I win $1, then I'm going to invest $10 on the next day. That is my strategy. And if I lose $1 on the first day, then I'm just going to stay put. I'm not going to do anything on the second day. Okay. So now, in this, so yes, if x1 is equal to -1, so if I lose $1 on the first day, then I know that on the second day, I'm just not going to invest anything. So first day I will invest $1, maybe I lose that, and I'm just not going to do anything. On the other hand, if I win $1 on the first day, then on the second day, I'm going to maybe invest $10, and I will either kind of have the stock go up. So so I may win or lose those $10 or something, depending on what the market does. I'm not really writing down what is the cost per share, etc. But let's say the cost was 1 per share, or maybe. So, but here, it's not that how x2 behaves is independent of x1, in the sense that if I tell you x1 is equal to 1, then the probability of x2 being n is half. If I tell you that x1 was equal to -1, then the probability of x2 being n is 0, because x2 is just always 0. I know for sure. If I lost one day, I just go home. Okay, so the random variables are not independent in the sense that the events that the random variable x1 takes value 1 has some effect on the events that the random variable x2 takes value n or -n or 0. It has the value of the random variable x1 has some effect on these events. Does that answer your question?
Yeah, I'm clear. Thank you.
Right. So what I think you were trying to say is that the expectation of the random variable x2 is 0 no matter what the value of the random variable x1 is. Because if I have some n dollars invested, the market will go up either by +1 or -1. So I will kind of either gain a certain amount or lose the same amount. So the expected gain is 0. And let's say my investment in stocks at time t is denoted by some number s, then my gain given any investment I might have, and this investment itself might be a random variable, right? Because how much I'm investing depends on what happened to x1. So what I'm investing at time two. So it might itself be something which is not fixed. It's a function of the outcome space. But conditioned on whatever happened up till time t, in some sense, the expected gain at time t is equal to 0. I don't quite know how this random variable s, or sort of how this event s changes, and how I don't know sort of yeah. So formally I need to condition on an event. So let's say I condition on that I have s dollars invested at time t. And no matter how many dollars I have invested at time t, my expected gain is 0, because I will kind of lose that sort of on each stock. I will either gain $1 with probability half or lose $1 with probability half. So the expectation. What is the probability that I have s dollars invested at time t? Who knows? I mean, I could have a very weird investment strategy, which again looks at all kinds of behavior of stock market in previous days, looks at the weather that day, sort of looks at what side of the bed I woke up on. Who cares? But conditioned on whatever, the expectation of x sub t is 0. So that means that expectation of x sub t, which can be written as a sum of conditional expectations, that the probability that I have s dollars invested times the expectation of xt given that I have s dollars invested and I know that this is always equal to 0. If you tell me how many dollars I have invested, conditioned on that, the expected gain is 0. These are just some numbers. So the expectation of x sub t is equal to 0 because of the law of total expectation. And by linearity of expectation, the expected gain is 0. Okay. So that's probably a theorist's view of the market. If I knew better, I would probably be a trader rather than a theorist. But this is at least my naive understanding if I didn't know anything better about the market. Okay. Any questions?
So if the probability of going up and down by $1 is not 1/2. Will that change the whole process?
Absolutely. So if it was, let's say the probability of going up was 60% or 0.6 and the probability of going down was 0.4, right? Then I would know that if I have S dollars invested, let's say each share is $1, then with the probability 0.6, I would have $2 at the end of the day, and with probability 0.4, I would have $0. So in expectation, I would have 1.2 times S dollars. And overall, yeah, it will also depend on the investment strategy. But if I keep investing more and more, I will keep getting more and more in expectation. So, and roughly, this is if you know that this is why people invest, I guess, in mutual funds or something, that if you know that on average there is some probability, higher probability that it will go up than compared to going down, then in expectation you will gain by investing more and more over time. And that's, yeah, I mean, we're not necessarily modeling that right now. It's a bit more complicated. But if it was not half each, then the expectation of X would not be 0. It would be some non-zero number, depending on what were the probabilities of going up or going down. Okay? And possibly depending on the investment strategy, maybe someone knows how to take advantage of this better, and so on. So, but just saying, at least in the simplistic view of the stock market, you don't gain anything no matter what investment strategy you use. Is that
I was just trying to clarify. So that equation X equal to X1 plus X2 plus 2X x5, more accurately is written as the expectation is actually X conditional on some strategy.
right? But we are summing over all the events that the probabilities of all events that at the end of the day, whatever our strategy did, it invested S dollars at time T. Okay. And this probability could be arbitrarily complicated. This probability could really depend on what our strategy is and what happened previously, etc. So, and if this was not 0, if the expectation of XT conditioned on this strategy was on S dollars invested was not 0, then it would really matter what these probabilities are and how they compare to each other, whether our strategy is more likely to invest $10 or $5 or $20. So it would matter. But so then the expectation of XT is really a function of this strategy. I cannot really tell you some blanket thing about it without knowing the strategy. I mean, naively, even if you knew that the stock market is going to go up for sure, the probability that goes up by +1 is 1. But if my investment strategy is that I'm just not going to invest, then I don't gain anything, because no matter what the market does, if I don't put money in it, I'm not going to get anything. Right? So on the other hand, if my strategy is that I'm going to put $1 million in the market and I know that it's going to go up, then tomorrow I'll have $2 million. So it's a function of both what the distribution of the market is at any, or the stock is at any given day, and my investment strategy. But in the special case, when the behavior of the market is completely random, it goes plus or minus 1 on any given day, the strategy doesn't matter. Does that explain?
Yeah, exactly. Thank you so much.
Okay. Okay, so let's maybe stop at this point. I'll leave this as an exercise to work out, that if you have two random variables that are independent, and independent in this way that for every value they can get, the events of that capital X is equal to little x and capital Y is equal to little y are independent events, then expectation of X times Y, which is just a new function where I multiply the values pointwise, or a new random variable, is equal to the expectation of X times the expectation of Y. That's something to check. And then also think about, is the converse true? If I have that expectation of X times Y is equal to expectation of X times expectation of Y, then is it the case that the random variables are independent? Think about it. We'll talk more about it in the next lecture. Let's stop here.